Dear students, in this video I will explain solution to this problem. So first read and understand this problem. A three-stage centrifugal pump has impeller 400 mm in diameter and 220 mm wide. So it is a three-stage centrifugal pump. They have mentioned it is a three-stage pump, but not mentioned whether it is a pumps in series or pumps in parallel type. So I am assuming here pumps in series type, pumps in series, because I haven't mentioned anything here. I'm taking pumps in series. So the vane angle at the outlet is 45 degrees, that is 5. The vane angle at outlet means the angle the relative velocity makes the tangent of the runner, that is 5, that is 45 degrees. And the area occupied by the thickness of the vanes may be assumed 8% of the total area. Area occupied by the vanes means suppose is the inner diameter, outer diameter. So now these are the vanes. Okay. So if you means at the outer periphery means this is the inlet and outer periphery will be the outlet point in the impeller. So this is the smaller area occupied by each of the impeller. So if you sum up all these areas, so it will be 8% of the total peripheral area. So for if you know the outer diameter, the peripheral area and the outlet will be perimeter into width of the impeller pi db. So 8% of this is 0.08 pi db. So pi dB, this is the area occupied by these impellers at the outlet. Okay, so this is given here. If the pump delivers 3.6 meter cube of water per minute, okay, discharge is given per minute when running at 920 rpm. Determine power of the pump, manometric head, and specific speed. Okay, specific speed of the pump. Power of the pump means what capacity of the pump required. Okay, is asking here to deliver this much water, right? Now mechanical efficiency is 88% and manometric efficiency is 77%. First, let's solve this data here. So it is a three-stage pump. So n is equal to 3, number of stages 3, diameter of the impeller at outlet. So in the problem they haven't mentioned whether it is a inlet dia or outlet dia. So but he has taken it as a outer dia because we needed the outlet diameter. So it is 400 mm and 20 mm. So phi is equal to 45 degrees given. So remaining all things, but discharge here 3.6 meter cube per minute, that is 0.06 meter cube per second. 3.6 by 60, so per second we'll get remaining things. So to solve this problem, we need the velocity triangles. To solve this problem, we need velocity triangles. So assume the curve is it is backward vane. So if nothing is mentioned, you assume the backward vane. So for the backward vane, the velocity triangle will look like this, whatever you are seeing in the screen. And VW2 generally, VW1 not 2, VW1 is 0 because the flow at the inlet will be radial for the impellers. So VW1 will be 0. V1 is equal to VF1. Here that means alpha equal to 90. Flow is radial, alpha is 90. That means V1 equal to VF1. VF1. So theta is inlet vane angle, phi is outlet vane angle. It is given. And remaining peripheral velocity at outlet, velocity at outlet, and remaining power. Okay. So this is how the velocity triangle look like if you draw. So then, so first thing we have to calculate the power of the pump. Power of the pump. So power of the pump. How to calculate that? We have the manometric efficiency and the mechanical efficiency. So overall efficiency we can calculate, that is 67.76%. So overall efficiency, so that will be manometric means the power developed by the water, means whatever the actual power it is given to the water by the impeller, that is WQ into H manometer, rho G Q H, rho G Q H manometer. So this is the power given to the water by the and divided by the shaft power. The shaft power. That is the power of the pump, right? So this is the overall efficiency of the pump. So from here you can calculate power of the pump will be WQH manometer divided by overall efficiency. But we don't know this H manometer. Okay, manometer head we don't know. Q is known and the specific weight of the fluid is 9810. H manometer we don't know. So first we have to calculate the manometric head, then we have to come back here. So how to calculate the manometric head? So use this velocity triangles from here, right? So if we want to calculate the manometric means the head developed by the impeller, that is work done per Newton weight of water, that is head developed by the pump. So H manometer head will be VW2 U2 by G. So if you know the overall means the mechanical efficiency, the manometric efficiency, it is we have to multiply with manometric efficiency because manometric efficiency will be H manometer divided by means actual head developed by the means given by the impeller to the water divided by VW2 U2 by G. So H manometer will be manometric head multiply with VW2 U2 by G. Okay. So this is what this is the equation. So we know the manometric efficiency. We don't know VW2. We don't know U2. If you calculate this, you can calculate H manometer, right? So how to calculate these two things from velocity triangles? See here. So you want this VW2 component. You know want this U2 component. Calculation of U2 component is simple. U2 is equal to pi d2 n by 60. Very simply, you can calculate this. So, and if you want to calculate this VW2, you need this beta value and the VF2 value, V2 value, or else if you are able to calculate this component, then U2 minus this component will give you VW2. Okay, so suppose for example, if this component is X, we have to calculate this X, U2, VW2 will be U2 minus X. So, how to calculate this X value from the given data? If you observe, we have this outlet area. So that is outlet area, peripheral area. I've, I've told you how to calculate the peripheral area. That is pi dB. Area occupied by the veins is 8%. So the net area available for flow will be pi dB minus 8% of pi dB. Okay. So pi d that is pi d2b 2 minus 8 by 108 percentage of pi d2b2. So this is the net outlet area available. So we have the discharge value given. So that is 3.6 meter cube per minute, that is 0.06 meter cube per second. So outlet will be 2.59 meter per second. That is VF2 velocity of flow at the outlet. This is the procedure how to calculate. If you know the discharge and outlet area, you will get the radial velocity of the flow that is at the outlet that is VF2. Okay, VF2 you can get this value. Right now you know this phi value 45 degrees, you know VF2. So can we calculate this X value? So tan phi, so tan phi is equal to VF2 by X, VF2 by X, X is equal to VF2 by tan phi, VF2 by tan phi, X is equal to VF2 by tan phi. So VW2 is equal to U2 minus VF2 by tan phi. So VF2 is known. Just now here they have it is calculated 2.59 meter per second. Tan phi is 45 degrees is 1. So VW2 is U2 minus VF2 by tan phi. So 16.68 meter per second is the well velocity at the outlet, right? So U2 is known, U2 VW2 is known. Manometric efficiency is 77% given the problem, that is 0.77 fractions. So total head developed by the impeller is 25.23 meters. So head developed by the one impeller, okay, whatever you have calculated just now. So this is for one wing, that means for the one impeller, it is 25.23. So in the starting of the problem, we assumed the pumps are in series, that means it is three-stage pump, and assumed pumps are in series. So manometric head will be 3 into 25.30. So if you want a head, discharge will be same for pumps in series. Discharge will be constant, and the head developed will be number of stages into head developed by the runner. Okay. So this is the total head developed by the pump, 75.69 meters. So this is the manometric head, total manometric head, right? So once we have this, so power of the pump is very easy. Just now means first I have explained this only. So H manometric head total by efficiency. So the power of the pump, that is 65.75 kilowatt. This much power you have to give input to the shaft. Okay, this is the input to the shaft. This much power is required. So next, the third, they have asked to calculate specific speed of the pump. So Ns is equal to n root q by h manometer power 3 by 4. And remember, here h manometer will be head developed by one impeller only, not the all impellers. So you cannot use the total head while calculating the specific speed. You can use only head developed by one impeller, right? So specific speed means the speed of the runner. Suppose the runner is delivering 1 meter cube per second against 1 meter head, then the speed at which the runner rotates will be the specific speed. So that is the definition. So we have to use the head developed by one impeller only. So this will be n root q by h m power 3 by 4, 3 by 4. Manometric head calculated is 25.23 for the impeller. So specific speed will be 20. Ms will be 20. Thank you.